My name is Seong Jin from TPS Cosmology Group. Today I'd like to talk about some interesting galaxy population which are observed by infrared telescopes. So, as Thomas said just before, in order to understand the cosmic star formation history of the universe, we have to understand infrared luminous population. That's because the infrared luminous galaxies are actually kind of star-forming systems containing a large amount of dust. So in these galaxies, newly forming stars are surrounded by dust. So more than half of the energy released by newborn stars are absorbed by dust and re-emitted in the infrared. So we are, so images, observation images looks like this. And we are interested in the infrared properties, especially, for example, total infrared luminosity, normally determined by the fine infrared data, and mid-infrared properties, for example, like 8 micron luminosity, representing the polycyclic aromatic hydrocarbon, which we say pH or PA, or star formation activity. For example, star formation and star from stellar mass. So among these galaxy parameters, total infrared luminosity is one of the most interesting and important parameters, especially in infrared galaxies. So the relation between the total infrared luminosity with the other galaxy parameter is always an interesting issue in modern astronomy. But in this work, I just simply focused on 8 micron luminosity, because the mid-infrared spectra of normal galaxies are dominated by PA features. So that means I'm interested in overall strength of PA features. So these PA features has been quite a mystery, but most of the people believe that this PA feature gives kind of very significant clues to the interaction between the star formation activity of a galaxy and overall strength of the PA luminosity. So this is also, Thomas said just before. So people observe the north elliptical field to get this kind of results. So we use the Hershel. So where is the laser button?
The middle one?
The middle one?
Yes.
It's too faint. So people use the Hershel and AKARI space telescopes. So Tom already talked about this. We, more than 10 years ago, we obtained this AKARI data. It covers a 5.4 square degrees. And we have more than 100,000 infrared sources. But also we use the Hershel space telescope, and it covers 9 square degrees and completely covered the previously observed 5.4 field. But in this field, we only obtained 4,800 sources. But besides this, we also have a large amount of ancillary data. We also have optical near-field data from various ground-based observation. But thanks to the spectroscopic survey, we obtained, Sim et al. In 2013 obtained 1,700 objects. But now at this point, we have already received information for more than 3,000 objects. But in this work, I used only this spectroscopic version. We also used the solar ages data, as Thomas said. And 2017, this SCUBA 2 survey was started, and it's still going on. So in this work, I use all of this data. So the starting point, I used the SPY catalog and made the spectroscopic redshift, and also I combined with the AKARI and NPY data, and as well as this ancillary data. So this map shows a kind of distribution of our sources. So this blue cyan dot shows 250 micron detected sources. It's 4,800 sources. And this field dot with various colors shows the distribution of 300 objects matched with the spectroscopic redshift. So right panel, right table shows the number of sources as a function of redshift bin from 0 to 4, also according to the types. So among these 300 objects, we just used 250 star-forming galaxies. So we used the sample to classify the galaxies at this low redshift range. So to understand the properties of this sample, we used a lot of color diagrams and BPT diagrams, something like that. So I think I don't have much time to go into the details, but this color diagram shows that our sample is mostly star-forming galaxies having PAR features, and also our So most of our sample appears to be normal star-forming galaxies or spiral-type galaxies, and they are mostly peak. Most of them are peak in the low-type galaxies. I can talk about it later. So after we understand our sample, we carried out modeling by SED fit. So this slide shows how these two megafields works in a schematic diagram. But the point is that this modeling uses in the infrared PAR emission features and very small grain and a little bit larger and coal dust components actually divided by these two components. So in our modeling, actually this kind of PAR infrared peak is described by two dust temperature model. So this is kind of SED fit results. So we checked our SED fit result in this observational frame or rest frame like this, and we compared with our latest SED fit result with the previous result, and finally we confirmed that our SED fit result is very good. So as you see, nicely reproducing throughout our photometric data points, our models describes our observed data points very well. And this is a kind of a relation between the output parameters, like number of sources as a function of redshift or total infrared luminosity as a function of redshift. So in more higher redshift, we have more higher galaxies. And in terms of redshift, our sources peaks around 0.3. And in terms of total infrared luminosity, our galaxies peaks at around 10 to the 11 solar luminosity. So this is a kind of low-type galaxy. So we mainly focused on the star formation rate and as a function of stellar mass. But we used a lot more physical parameters like dust mass, FMU parameters, total infrared luminosity, or 250 micron luminosity. So finally, we concluded that so this is one of our interesting results. So left panel shows the 8 micron luminosity as a function of total infrared luminosity. So it doesn't show quite good tight correlation. So this is one-to-one relation. So this result shows that and more luminous galaxies have some shortage of 8 micron luminosity. This means that PAR features in bright luminous galaxies are destroyed by star forming activities. Like the star features are destroyed by actively star forming region. The strong radiation from the actively star forming region. And right panel shows the specific star formation rate as a function of redshift. And the color shows the stellar mass. So this red color shows the most massive galaxies. So in a certain redshift range, the most massive galaxies have a less star formation rate, so which means that the most massive galaxies have does not have enough gas compared to the less massive galaxy, because in the early epoch they used up the gas more violently because they made a more actively stars in the previous epoch. So they used up the gas more violently. So we can see this kind of trend. So this is also known as the downsizing trend. So these two results are our main results. So one is power emission deficit phenomena, and the other one is a kind of observational confirmation of downsizing trend. So this is a summary. NEP spider sample are 250 micron counterpart of our mid-infrared galaxies, and we can see the power deficit in the luminous galaxies. But this power deficit phenomenon is normally reported at higher redshift. But in this study, we can see this phenomenon at a very low redshift range. And our power galaxy shows the downsizing evolution pattern. Yeah, that is all.
Any questions? Yeah. Your pi emission that usually comes from the PDR region, partially dissociated region. So if you have very strong UV radiation and gas is totally ionized, pi can be destroyed. So the infraluminous galaxies might have like top-heavy initial mass function, or it's just in the evolution stage where the UV flux is dominating to destroy all the pi. Is it possible?
So you mean we have to compare with some kind of UV data?
You won't. In general, I just don't think PAH is a good indicator for star formation.
Yeah, in this case, in this case we can say like that. People thought that
24 micron might be a lot better.
24 micron.
Yeah, you need continuum, not pH is not reliable.
So when I got this result, I was really wondering about if you can say like that, now 8 micron luminosity and total infrared luminosity, the relation between these two, 8 micron luminosity and total infrared luminosity, is a quite good indicator of star formation activity or not. So anyway, we just reported this to the AKARI special issue and accepted last year, but still, I think it's still in question. I think we need more data.
No, I think there's just no physical reason for them to be correlated. 24 micron is just dust emission, that's simple. But pH, you require pH to be present, and it can be destroyed by UV radiation.
Yes.
I think that's a naive interpretation of this.
This is a very naive interpretation, but there's one more reason. Without any radiation from the star formation region, if there's a very large amount of coal dust in the ISM, that might cause a large total infrared luminosity. This can be also make
It's just,
the further.
I don't think pH emission is a reliable indicator for star formation.
yes. That's right. I mean, okay. He fine thread, so he's comparing and then try to see the quantify and then understand the reason.
Yeah, you just said that more observations are needed. I think, if you think it's not a good indicator, even more observations are not going to help.
Yeah. So it's my talk that I was trying to use it the indicator because I didn't have fine thread, but he does have fine thread, so he's comparing.
I think this is also kind of selection effect. We have to match fine thread data and medium thread data to see this kind of features.
Okay,
If we do not use the fine thread data, maybe we cannot see this kind of properties.
Okay, let's send the speaker again and we need to move on.